So here's section 5.4, and this is theorem 5.4.1, which is I think a very interesting theorem. So if f of z is a polynomial, and now here's the important part, with real coefficients. Okay, then the non-real roots, okay, the complex roots, occur in complex conjugate pairs. Okay, conjugate pairs. So you see, and so they say, for instance, if f of z equals 0, then f of z conjugate equals 0 is what they're saying. And or another way to say it, if z is a root, z equals x plus iy is a root, then so is well, I won't put a z equals x minus, try to get that right here, x minus iy is a root. And it's a pretty nifty little proof. It uses the fact that 0 is real. So here's a proof. And so we set up, I'm not going to go through their whole setup, but it is pretty short. We're working with this f of z with real roots. Then it says, okay, and we'll see where the real coefficients come in. We have 0 is equal to 0 conjugate, because it's a real number. But so if we've got a root, then 0 conjugate is f of z conjugate. Okay, so we used a z that was a root of f, and we got 0, but we can take the conjugate of that, and that's still 0, and so we've got this identity, and then, well, so that equals, if I take the conjugate of f of z, then I use some of those rules, and I have an an z to the n conjugate plus, so we sort of, going from here to this next line, we use the fact that we can separate a conjugate, the sum inside a conjugate to the conjugate of the sums. So then a n minus 1, z n minus 1 plus dot dot dot, and that's a conjugate all the way to our a1 z conjugate plus a 0 conjugate. But then we can do those separately because they're a product, so that's an conjugate z to the n conjugate plus an minus 1 conjugate z to the n minus 1 conjugate plus, all the way to a1 conjugate z conjugate plus a 0 conjugate. Then we can, since the a's are all real, so that's where this matters, that the a's are all real, we have an, and then z to the n is just a product under the conjugate, so I could then move that conjugate inside that power of n, and then plus a n minus 1 z conjugate to the n minus 1 plus, all the way to a1 z conjugate plus a0. But you see, that's just f of z conjugate, and so we get 0. So that's a nifty proof. Okay, it's just using all those properties of conjugates. And then they mention this example, example 5.4.1. And so they say, discuss the positions of the roots of the equation 5 z to the fourth equals -1. And so notice this is a polynomial. I can say, oh, this is f of z equal z to the fourth plus 1, and I'd like to set that equal to 0. Well, according to this, everything is complex conjugates. And so if I'm thinking about the position of these things, wherever they go, they're going to have to be, if one's there, then I have to have one there. If, say, one is here, I would need one there. Okay, if I had a real root, now I don't, because notice, it's z to the fourth is -1, so no, I'm not going to have any real roots on that. But, if I had a pure imaginary root, then it would have to be one up here and one down there. Okay. Actually, the roots are going to look more like what I drew for the first 4. And so they go a little bit further with this, and they say, well, if z is a root, so is -z. Okay, so notice that that's the other part of this. So I went with the complex conjugates, up here, down there, but then they also point out that if z works, if f of z is equal to 0, well, then so would f of -z be 0. And that's just real numbers at work, right? Is if I take -z to the fourth, I get the same thing as z to the fourth. And so that's why, I say that when I drew these first 4 like this, that's what's going to happen, because if that's a root, so that's z, then that's -z, and that's z conjugate, and that's -z conjugate. Okay, so my roots would all look like that. Okay, somehow they would make, these sort of 4-corner looking things. Okay, so that was their example that went with that 5.4. So there's our theorem. What the heck theorem was that? 5.4.1.